So today we're going to talk about multithreading, which is an important form of parallel programming. And I want to start by going over why do we want to do this, and then get into the how. So to understand why multithreading is important, we have to look at what's happened with computer architecture in recent years. So let's go all the way back to 1978 and the first PC microprocessor, the Intel 8086. It had 29,000 transistors, ran at 5 megahertz, and it took about 10 clocks to finish a single instruction. So you'd fetch the instruction, you'd decode what it means, you'd execute it step by step. So about 10 clocks to finish it. So on average, it could complete about 500,000 instructions per second. Now, if we move forward to the processor that is inside the UG machines you're using, it's an Intel Core i7, which isn't all that informative because Intel calls lots of chips Core i7. Its code name is Haswell. That's actually a better description of what it can do. It contains 1.5 billion transistors. It runs at 4 gigahertz. It takes actually somewhat more clocks to finish an instruction. So it takes about 15 clock cycles to complete an instruction. Part of how we're getting this higher clock frequency of 4 gigahertz is actually do less in one clock period. But it more than makes up for that by having about 30 instructions in flight. So while it takes 15 clocks to finish a single instruction, it's working on about 30 different instructions at the same time. The net impact is that it completes about 2 instructions in the typical clock period. If we multiply these things together, we get about 8 billion instructions per second, which is a huge increase over what we had in the original PC microprocessor. Now, beyond what we get out of one CPU core, which is what I just described, the transistor budget is so large nowadays that the UG machines have 4 different CPU cores. So 4 different processors, basically, as well as systems to talk to I/O. So talk to memory, talk to other I/O like PCI Express, an integrated graphics processor that's good at things like pixel processing to draw stuff on your screen, and some on-chip memory called a cache, which basically stores recently accessed data because the processors are so much faster than memory. Okay, so let's look at what's changed then over that 35-year or a little less than 35-year period. We got 50,000 times more transistors, so a huge increase in transistor budget, and we're able to turn that into a very large increase in the number of instructions we can complete per second, 16,000 times. So huge gains in the performance of a single processor core. Now the future looks a little different though. So we are still getting about twice as many transistors every 3 years, so we can build a lot more on chip, but the transistors are not getting much faster. If you go and buy a processor today, in 2021, you'll find that it runs, if it's a high-end processor, about 4 gigahertz, which is the same as the UG machines, which are a few years old. So we're not getting much more CPU clock speed. We can do a little more instructions per cycle. So the Haswell processor that's in the UG machines can do about 30 instructions at a time, or it can work on 30 instructions at a time. You can work on even more instructions at once, and that can allow you to complete more instructions per clock cycle. But the complexity to do that, the amount of transistors, logic to do that, grows very rapidly. And more importantly, the power grows very rapidly. You need a lot of hardware to figure out which instructions can be working on, make sure that while the processor is working on 30 things at once, to the programmer and to the person debugging the program, it appears that every instruction completes in the same order you wrote it in the program. That actually takes a lot of power, a lot of hardware complexity to make that happen. What this means is that because we're getting lots more transistors, we are still increasing the number of instructions we can complete per cycle by working on even more than 30 instructions at once, but it's a slow growth. So the latest processors, instead of completing, say, 2 instructions per cycle, they might be completing 2.5, maybe a little more than that, but it's a slow growth. So what's the impact of this? CPU speed is still improving, but not very much anymore. So for many years, it grew very rapidly. Now, a single core is not getting much faster as you move to the next generation of manufacturing technology. On the other hand, we are still getting this huge increase in transistors that we can fit on a chip. So what are processor vendors like Intel and AMD and Apple doing? They're putting more and more processing cores on a single chip. So we're not getting cores that are much faster than we used to, but we are getting more of them. The UG machines have, well, if you go back to the original PC processors, it was 1 CPU on a chip. The UG machines are 4. If you go buy a machine today, you could easily get one with 8 or 16 cores. So it's gradually increasing. Multi-threading, well, so what can we do with those different cores? Well, we can run a different program in each one. So you can now have a computer that can run many programs at once. So maybe we have multiple people logged into the UG machines, or you're doing 2 things at once. That's useful. But we'd also like to be able to take one program and run it faster, because often we don't have a lot of different programs that can keep all of these cores busy. And that's multi-threading. Multi-threading is we want one program that is using multiple cores to get things done faster. All right, so this has really been pushed by where computer hardware is going. Now, let's look at how this works. So the programs that you've written so far in your career at U of T have been single-threaded. So you have a CPU or a core. I'm going to use those terms pretty much interchangeably. And the key things that exist on that core from a programmer point of view are it has a program counter. So it points to some instruction that it's going to execute next. And it has a stack pointer. And the stack pointer points to some region of memory where all your local variables are. In memory, we have, as I said, a stack that stores all the local variables for your various functions. We have all of the instructions that are the code of your program. What is it going to do? We have global variables, and we have what are called heap variables. Heap variables are everything that you created with new or malloc. How does this change when we move to a multi-threaded program? Well, a bunch of things stay the same, right? We still have, well, let's start with what changes. So instead of 1 core, we now have 2. If I've got a program with 2 threads running on 2 cores. Each of those cores still has its own program counter, still has its own stack pointer. What does that mean? It means that each of these cores can and generally is executing a different instruction. So this core is executing a certain instruction, this other core is executing a different instruction. So they're not at the same place in your program. They also each have their own stack. So each core has got a stack pointer pointing at a different region of main memory that stores its stack. So that means core 1 gets a certain image of the local variables, a certain set of local variables, and core 2 has a different stack. It has different local variables. What they do share, though, are the actual program. So while their instruction or program counter points at different instructions that they're executing, they are both looking at the same program. They share the global variables. So those are all in common. If one of them updates it, the other one sees the update. And they share the heap variables, the variables created with new. As long as you have a pointer to it in core 1, and you also have a pointer to it in core 2, both of these could access the same variable that was created with new. Okay, and basically, if we run 2 threads, meaning that each of these is running a different instruction, these 2 cores can collaborate to run this program faster. Okay, so just to summarize that, each thread has its own program counter, so it can be executing a different function, and it is almost always executing a different instruction. So that instruction might be in a different function, but it almost certainly is in a different line of your program than threads on different cores. Each thread has its own stack, so it has its own copy of local variables. And each thread sees the same global variables, and dynamically allocated memory is shared by all the threads. So if multiple threads have a pointer to the same memory that was created with new, they can both access it. What does this mean? Well, the good news is that means threads can communicate through memory. They can use global variables, dynamically allocated memory to one updates the variable and another reads it, they can communicate really fast. This is much faster than communicating over a network. However, this comes with some things you have to be careful about. So because the threads share global memory and memory that was created with new, you can have problems where two threads, for example, update the same global variable at the same time. So if I have a global variable, so int my global, and I have a certain thread, so thread 0 basically says my global equals 1, and thread 1 says my global equals 2. These conflict. They're both trying to write to the same memory address, the same exact variable. So one of these threads is going to overwrite the change that the first thread made. You don't know which one, and it can be confusing. If there was then an if statement, if my global is equal to 1, do something, well, you would expect this if statement is going to trigger, but it might not if this other thread over here actually changed the global variable between this instruction and this instruction. So you got to be careful, particularly with global variables. Multiple threads could be updating them at the same time. Finally, you can have more threads than CPUs. So I've basically talked about the UG machines having 4 cores, so it's useful to run 4 threads on them and get more work done. You could also create more than 4 threads, and that's fine. Your program won't crash. The operating system will basically time share the CPUs. So you won't get more work done because there are only 4 CPUs. Those threads will basically be swapped in and out to do work by the operating system. So it's legal, but not really beneficial in terms of getting more work done to have more threads than CPUs.
Okay, so let's talk about multi-threading libraries. So when you write a normal program, your program starts one main thread. So in C++ and C, execution starts in a function called main, and main actually starts a thread. And so far, all the programs that most of you at least have written have just used that one thread. If you want more threads, you have to create them with some kind of application programming interface or library. And you've got a few options to do this. So one option, and the one we recommend if you want to explore multi-threading in this course, is called OpenMP, Open Multiprocessing. OpenMP is based on compiler directives. So compiler directives, they look like this. Okay, so hashtag pragma. That basically means this is not code. This is an instruction to this is a command to the compiler. And if the compiler doesn't understand this pragma, doesn't know how to speak that, it just ignores it, and your program will still work. All right, so this is extra instructions to the compiler. All of the OpenMP pragmas start with the word OMP, OpenMP, and then they say, what are they? So this is a particular one called parallel for. So this pragma tells the compiler there's going to be a for loop right after this line, and I want you to execute that for loop using multiple threads working in parallel. So divide the work up, send it to multiple threads to speed up my program. That's pretty succinct, right? So with one line of code, I told the compiler, make the for loop after this parallel. The compiler we're using in the UG machines, G++, supports OpenMP, so it understands this line, and we've set up the makefile so that it'll all build properly. If you were to run this code on a compiler that doesn't support OpenMP, it will just ignore this line, and your program will still work. Just won't run as fast because it'll run this normally on a single thread. Okay, it's not your only option. You can also use something called C++ 11 threads. So this is part of the C++ standard library. The reason it's called C++ 11 threads is it was added to the standard library in this revision of the language. They give you more control. So there are times when this is an appropriate choice, but they make you write more code. So OpenMP is kind of high level. You don't have to write as much code. What does it look like? So I'm not going to teach you very much about C++ 11 threads, but you can certainly look them up on the web. You include the threading header. So you include thread. And then you do things like this. In my main function, for example, I could say, I want to make a variable of type thread. So that's defined in this header. You give it a name. So this is just a variable, my thread. And its constructor takes the name of a function. And basically what will happen is this will create a new thread for you with this name. And that thread will start executing in this function. So it's not that hard to create a new thread using this either. And to control exactly how your threads interact, there are more objects and methods that you can use. But we're not going to talk about those because it is more code to get this going. Third popular technique is called p-threads. P-threads is actually the same as C++11 threads. It's a C API that is older than C++11 threads. C++11 threads basically makes the syntax easier, is a little bit higher level than p-threads, and is actually built on top of it. So I would say I wouldn't write p-threads code. I would just write C++11 threads instead, because it's a bit easier and it's going to give you the same amount of control. All right, so we're going to focus on OpenMP because it's the highest level of these APIs. So it's going to be the easiest for us to get a code going. And I see a question. Yeah, so Trevor, maybe I'll hold those questions about OpenMP until the end of the lecture. Some of them I think will be answered during the lecture, and some will probably make more sense to the rest of the class when they've seen the basics. Okay, so here's a little program. So here's my main program. I make a couple of vectors. They each have 100 entries, so A and B. And then I've got a for loop where I'm going to go through the entire vector, and I'm just going to compute, I'm going to update my A vector to be the sum of that A entry plus the B entry. Okay, so pretty simple. It's like a form of vector addition. After that for loop, I'm just going to walk through the whole A vector, my output vector. I'm going to print it out. So I'm going to print out every entry in my A vector, and that's the end of my program. Okay, so nothing too exciting. Okay, so how would I convert this to use multiple threads? There's a skill testing question. I haven't taught you very much OpenMP, but I showed you enough on the prior slide for you to convert this to use multiple threads. Okay, so split up I see a couple of comments, split up the for loop and use a thread for each piece. So that's the basic idea. I should split up the for loop and use a thread for each piece. But let's see, get rid of this, sorry. Exactly what's the syntax to do that? Okay, so what do I do in OpenMP? So I see Isidore saying it's not worth it. The overhead to start a thread is too high. That's actually true. Okay, so there is an overhead to start a thread. So for this small amount of work, which is just adding 100 numbers together, it's not really worth it to create another thread, but I want to do it anyway to basically show the concept. And yeah, Tahaz and Sweeney both have the answer of how we do this. So we can make these for loops parallel with just a single pragma. And I've got that on the very next slide. So all we do is in front of the for loop, we say pragma OMP parallel for. And basically the very next statement, which is this for loop, is going to be run in parallel. I have two for loops here. I want to make them both parallel. So I'm going to do this twice. I'm going to put OMP parallel for in front of this one as well. Now they'll both run in parallel. Okay. Now we have to think about what are these going to do? These variables were declared before, they're not local basically to this for loop. Okay, they are created before I enter the parallel section of code. That means that these variables will be shared by all of the threads. Okay, so I'm going to make A is going to be 100 entries, and they're all going to be initialized to 50. B is going to be 100 entries, they're all going to be initialized to 2. And those, when this is parallelized, I'm only going to have one copy of those variables because they were created before I got into this parallel code. Okay? These local variables, so this is a local variable int I, here's another local variable int I. Those are declared within the parallel block, the parallel for loop. So there will be a separate variable for every thread. Okay, so this is a kind of a key concept. You need to think, once you have multiple threads, you need to think about, do I have one copy of this data that all the threads are accessing, or does every thread have its own copy? And what OpenMP does is exactly what I said. Every variable that is declared before you hit the parallel section, you have one copy of. All threads share it. Every variable declared inside the parallel section, including variables, local variables, and any functions that you call, you've got a different copy for every single thread. Okay? All right, so this is, if I run this, this is actually the output I'll get. Well, so first, what should I expect? I'm adding up A and B, and every entry of A is 50, every entry of B is 2, so I should get 52 printed out for every single entry. So I should have A of 0 is 52, B of A of 1 is 52, and so on. If I run this program without multi-threading, that's what I would get. It's pretty boring output, but that's what it is. That's not what I get if I run this code with the OpenMP directives in it. I would get A of 0 is 52. That makes sense. A of 1 is 52. A of 2 is A of 25 is 52. A of 26 is 52. 52. This is real output that I got from running this program. What is going on here? This looks kind of bizarre. It doesn't look completely random. It seems a bit correlated with what I would expect, but it's obviously not perfect. So what has happened? So my first experiment with multi-threading doesn't seem like it's great. Yeah, so everyone who's answered this has basically got it right. So it's a race condition. It's multiple threads that are writing to the same variable without synchronization. So they're all printing at the same time and the order is undefined. Okay, so if I go back and look at this, I'm writing to cout. And cout is a global variable. So it is shared by all threads. And I now have multiple iterations of this loop executing in parallel. I've got multiple threads working on it. And it's chaos, right? They're all writing to cout at the same time. And they're basically interleaving their output. So it's pretty chaotic. Okay, so this is not a thread-safe thing to do. Remember, every one of these, we're making a bunch of calls to operator output, and we're randomly interleaving our output. Sarah's asking, what do you mean by cout as a global variable? So if you actually look in the standard library, you'll see that standard cout is a global variable. That's why you could just, all over your program, write to cout. Does that answer your question? So you didn't make that global variable, the standard library made it. One other thing I should tell you, which I glossed over a second ago, is the semantics of, they might have this on another slide. Let me see if yeah, okay, so let me show you what happened. So what did OpenMP do? It split the loop iterations across the threads, and it knows how many threads are on your computer. So it actually makes calls to so its underlying API in the operating system to ask how many cores are there, and it's going to be told there are 4 on the UG machines. So OpenMP is going to split that loop that went from 0 to 100 into 4 equal pieces. So it'll basically create 4 threads. Well, it already had 1 thread. It'll create 3 more. And each of them will be assigned a different range of the loop. So thread 1 is going to go from 0 to 24. Thread 2 is going to go from, 25 to 49, and so on. All right, and each of those threads will get assigned to a different CPU core, so they can all execute in parallel. And for the first loop that I showed you, this one, that works fine. It works fine because every thread is updating a different part of the A vector, a different entry in it, so there's no problem. Even though they all see the same A vector, they're all updating a different part of it, it all works fine. But the problem occurs here in the second loop where they're writing to cout. So I have 2 threads writing to cout at the same time, or 4 threads writing to cout at the same time. And what happens is just kind of chaos. They interleave their output. It doesn't really make any sense. Okay. And how do we fix this? So I see some interesting questions. I'll answer those in a second. How do we fix this? So to fix this, basically we need to make sure that only one thread is actually printing out at the same time. And we can do that with another OpenMP pragma called Pragma OpenMP Critical. What that means is the next line or block, if I want to have multiple lines, I can just enclose them in braces, right? Where I have line 1, line 2. Okay, so the next block of code, which could be one line or it could be something enclosed in braces, is basically only going to be executed by one thread at a time. So one thread will be allowed to execute this line of code. All other threads must wait. When that first thread finishes executing this line of code, the next thread can come in and execute it. All right, so they basically use something called lock variables, which OpenMP automatically creates for you when you create this Pragma OpenMP Critical to negotiate who gets to run the next block of code, but only one of them will run at a time. So what will the output look like after we do this? Okay, so so I said that. The idea is that it's kind of like you've got a speaker of the Senate or the House of Commons, making sure that only one person can speak at a time, right? So you have the floor, you have the floor, you have the floor. Only one thread will be able to execute this line of code. You will no longer get this kind of crazy output where you get things like A0 is, A1 is, etc., like kind of half completed lines being interleaved. You will still get things like this. A of 0 is 52. A of 25 is 52. A of 75 is 52 because we have multiple threads running. Okay, so we're not going to get the output coming out from 0 to 99 anymore because that's not actually the order in which the threads will hit this line. Each of them will print a complete line of output, but we still will be interleaved line by line. If that was a problem, then we shouldn't do this. But let's say in our case, we're perfectly happy with that. The code works to our specification if we do this. Okay. You do not want to put these critical pragmas, well, should I put these critical pragmas all over the place? What do you think? Is there a downside to them? So the upside is they enforce that only one thread can be executing some block of code, and sometimes I need that, like this output line. Is there a downside? Yeah, so you're all right. So various people are saying, yeah, well, you're going back to single thread. So that's exactly correct. If I put Pragma OMP Critical all over the place, then I might as well just delete all this stuff because I've wound up saying run this in parallel, and then I'm going to say, but not really. Make sure that you negotiate for the following block of code and only one thread runs it at a time. So you want to use critical sparingly. If you don't have to use it at all, that's best. You're going to get the best speed up. Sometimes you have just a little piece of code. Maybe did a lot of computation and you just got one little piece where the threads have to wait and make sure only one does it at a time. That's a reasonable use of Pragma OMP Critical. Okay, so that's basically what I just said. Let me go back and show you one last thing. Let's see, they said there was a question from someone about are we using 3 threads? And no, we're actually using 4. If we had 4 cores in the UG machines, OpenMP will automatically create 4 threads for us when we hit these parallel 4s. There's the last thing I should tell you. So what happens here is when we hit this for loop and we said OMP parallel 4, and let me go back here so that it's less messy. Basically at this point, 3 more threads created. So we'll now have 4. So we'll have 4 threads. Those threads will go through this loop. Each of them will get 1/4 of the work. Okay, so 4 threads divide the work. And what happens when we get to the end of the loop? So at the end of the loop, all of those threads will wait until all 4 are done. Because that's what would have happened in a serial program. In a serial program, you would have done all this work, and only after it was all done would you go on to the next block of code. That's what OpenMP does as well. So the threads that have been created will collaborate to split up the work in this for loop, but then they will all wait until everybody's done with their piece of the for loop. When all 4 of them have hit this point, 3 of them will disappear, and 1 will continue on, right? The main thread will go on to the next thing. When it hits this spot, 3 threads will be created again. So we have 4. Those 4 threads will collaborate to finish this, and then they'll all wait at the end of the loop until all 4 are done, and then 1 thread will continue on. So the style of parallelism we're getting is basically threads are created, they collaborate on a for loop, and then they wait at the end, and then 1 thread will go on when everybody's gotten there. Okay? All right, so hopefully that's clear. Actually, there was another good question. So sorry, one question I'll go back and answer here as well is someone asked, let me clear this off. What if the work, maybe I've got this on another slide. What if the work in this for loop, say this one, was uneven? You don't have to do this, but basically by default, OpenMP will divide up the for loop basically in equal pieces. So for this loop, if size is 100, it'll give, and you got 4 threads, it'll give 25 iterations of the loop to each thread. There are cases where there might be a different amount of work for each iteration through the loop. If you've got a pretty complicated loop, you can control that in OpenMP as well. So there's an optional keyword called schedule that you can specify. You don't have to do this. But that schedule defaults to static, which means divide up the work in this for loop by giving the same number of iterations to every thread. But there are other values that you can specify, such as dynamic. And dynamic, basically, OpenMP generates different code where the threads will effectively check what work is left to be done, so that if one thread finishes faster, that its piece of the work faster than others, it will go and grab more work. That's not the default. The default is static. The reason is if the work per iteration is even, static is more efficient because the threads don't really have to talk to each other to figure out what's the next thing to do. They just take a chunk of work and go off and work. But if you have a loop where the amount of work varies quite a bit, then the dynamic scheduling can be a better choice. And it's just two extra words to ask for that. So OpenMP, again, is giving you quite a lot of power. All right. So I'll come back to Isidore's question in a second. About, do we need to control for M4 the schedule? And the answer is you don't. But we can answer why in a minute. So and actually, Trevor's got a good question of, are there dangers to using OpenMP and standard thread in the same program? That's a good question. I've never tried doing that. It should be okay. You could create your own threads and then also have OpenMP creating threads for certain for loops and so on. So that should be fine, but I haven't actually tried it or researched it. Okay, so that was the abstract. How do we multi-thread things? Let's talk about what can we do in milestone 4. So we want to take something that takes a lot of CPU time. If it doesn't take much CPU time, there's no point. And if you see the tutorial from this week, you'll see that we used OpenMP to parallelize a loop that didn't have very many iterations and actually slowed down our program because there is an overhead to creating threads. So if you don't have much work to do, creating additional threads is worse than useless. It actually costs you time. So we want quite a bit of time. And we actually really want it to be, a lot of, ideally most of our CPU time, so we also get value for the extra effort we're going to put in. You also want the work to be independent. So independent means we don't have results that depend on earlier results, or we want to minimize that because that makes it very hard to multi-thread. When you have these dependency where you've got multiple things that are going to be updating the same data, we're going to need these OMP critical sections, and that's going to slow down our code. It's also going to make it a lot harder to make it work correctly. So we really don't want to have that. So what are the candidates? What do you think we might multi-thread in milestone 4? I can give you a hint. Nobody has any ideas. Yeah, so Isra says multi-thread the multi-destination Dijkstra. Wang says the greedy searches. So we got a couple ideas here. So greedy searches, multi-destination Dijkstra, those are both reasonable. I'd say where you want it, the lowest hanging fruit, the biggest gain for the least work is the pathfinding, the multi-destination Dijkstra. So if you have D deliveries, we're going to invoke a multi-destination Dijkstra algorithm about 2D times if you want to pre-compute all the paths and get the best travel times. All of those are doing independent work. They're basically starting at some intersection, and from that start intersection, they want to find the minimum travel time to all the other interesting ones. That's independent. It also is quite a lot of CPU time. So for the biggest problems we give you, you can use most of your CPU time doing this path search if you want to compute perfect travel times. So that's probably the biggest gain, lowest hanging fruit. You could also do multi-start of order optimization algorithm, which is basically, I think, what people are suggesting of multiple greedy searches. So it doesn't have to be greedy. You can basically just say, I've got some algorithm, could be greedy, could be iterative improvement, could be a mix of those two. And now I could basically start 4 copies of that algorithm with different starting points, let them go off and optimize, and when they come back, I'll choose whichever one got the best answer. And there's no dependencies between them because I'm just giving them a different start point and telling them to go off and do whatever they want. So if you had an algorithm that doesn't take very long, so greedy doesn't take very long, may not be worth doing. You could make it parallel, but it's so fast, maybe you don't care. If you have, on top of greedy, you have some iterative improvement that takes longer, now this might be more interesting. You could also do things like saying, well, instead of running the same optimization algorithm from 4 different starting points, maybe I could say I've got an iterative improvement algorithm and I'm going to try to do 4 times as many perturbations to get a better solution. But I actually want to do 4 times as many perturbations on one solution. So whenever I find a better perturbation, I update the solution, everybody starts working off that better one. You can do that. It's a bit harder because now you have one variable that is representing your solution, your delivery order. And whenever some perturbation in one of your threads finds a better delivery order, it's going to have to update that. And that means it's updating that something that other things are reading or might try to update at the same time. So you need some OMP critical to protect that order representing variable so that you don't have multiple things trying to change it at once. So that's more complicated. And it might actually reduce your speed up because if your threads are always waiting to be the one that can update the delivery order, then you'll lose some speed up. And more importantly, you have some extra room for bugs and complexity. You can do things like say, well, maybe I'll only update the best. Each one of my threads is basically optimizing the delivery order using iterative improvement. And they work for a while. And every once in a while, they basically say, if I've got some improvements, I'll just now update the overall delivery order. And that means I won't have to update it too often. And maybe that means I don't wait as long for other threads. So you could do that. But basically, this is kind of increasing order of difficulty, I'd say. And this is kind of the biggest gain, probably the least hard to do. This one's also pretty not that hard to do, but the gains may not be as big. And this last one is harder, where you've got multiple improvement algorithms that are all storing what is the best answer so far. All right. Okay, how much speed up can I get? So multi-threaded code is harder to write, it's harder to debug. So what's the payoff? Is this worthwhile? So let's say that I spend 60% of my time doing multi-destination Dijkstra, finding all those travel times, and I only spend 40% of my time trying to figure out a better order of deliveries. So I should probably, if I'm going to try to make something parallel, try to make this parallel first, because that's the biggest CPU time. So if I make it parallel, how much faster do you think you could make your program? So with these numbers, roughly how much do you think it'll speed up on our 4-core CPU? So I'll give you a second. If you think you know the answer, you can type it in the chat. So you think you make it about 15% faster? Okay, so 30% faster. Any other thoughts? 3 times faster. Okay, so we've got a wide range. Okay, so again, we've got a 4-core processor. In parallel program, we define something called speed up. So speed up is the wall clock time. So wall clock time means what you would measure on a stopwatch, not how much time we spend on all the CPUs, but just how long does it take before the program finishes. So the best speed up we can get is generally if the time it took if we ran on 1 core divided by the time it took. Well, this is the definition of speed up. Time it took if we ran on 1 core divided by the time it took if we ran on all the cores. Okay, and the best that you're going to get for that is normally the number of cores. Okay, they don't get in each other's way. They don't have any problems accessing memory. You get 4 times as fast a run with 4 cores. Okay, so let's just plug some numbers in there. So 4 cores, we expect to speed up at most 4, and only for this part, because that's the only part we're making parallel right now. So our total time is 0.4, which is our path ordering, 0.6, which is our pathfinding, and we're going to divide that 0.6 by 4. We add that up, we wind up with the total time is 0.55 of the serial time. So our speed up is basically the serial time, which is 1, divided by the new parallel time, 0.55, and we get a 1.8x speed up, so a little less than 2x, which isn't bad, but at first might seem disappointing. You might say, well, I used 4 cores, I attacked the biggest CPU time, more than half the CPU time of my program, and I got less than a 2x speed up. And this effect is important enough, it's given a name, Amdahl's law, after the mainframe computer pioneer, Gene Amdahl. It basically says you are limited by the serial code in your algorithm. The most speed up you can ever get, even with an infinite number of CPUs, it's limited by how much of your algorithm is serial. So even with infinite CPUs, if we only speed up pathfinding, we can never get a speed up higher than 2.5x for the particular case I've just given you. So Amdahl's law basically says it's harder to get really high speed ups than you think, because the serial code really limits you. If you can get rid of almost all the serial code, then you could get really high speed ups, but that's difficult to do. You usually wind up in most algorithms with some serial code that's very hard to make parallel. So you kind of take that into consideration when you decide, should I parallelize something or not? Okay, so we've talked about parallel pathfinding is a useful thing to do for milestone 4. Here's a gotcha to watch out for. So many teams will have written their pathfinding code, their Dijkstra or multi-destination Dijkstra, using something that looks like this. They have a global data structure that stores information about every single node in the graph, every single intersection. Okay, it doesn't really matter what's in here, but I've got a vector, so for every intersection, I've got some data. I might have what's the best time I've ever seen to that intersection, what's the reaching edge or street segment that I used to get there, and so on. And now I've got a for loop that basically I'm going to go from every start point to every interesting intersection I want to call my multi-destination Dijkstra algorithm. And I'm going to do that starting at every one of my interesting intersections. So I'm going to have a for loop that goes through all my deliveries. Okay. And I'm going to make it parallel. So I make it parallel with this Pragma OMP parallel 4. If I do this, is it going to work? Okay, so I'm reading what Isidore is saying here. Okay, so Isidore is saying, no, this isn't going to work. Okay, and it's not going to work because of conflicting writes. So yeah, this is a global variable, and it is declared before the for loop. So I'm going to have this for loop cut into 4 pieces, and I'm going to have 4 threads each working on a different set of start intersections. All right, so different threads will get different I values, but they're all sharing the exact same node data, which is what's the best time to this node, etc. But that means I'd have, this is my start intersection I equals 0, and I'm basically doing a search out in waves from it. And at the very same time, I might have I equals 1 is running on another thread, and I'm doing searches out from it in waves. And wherever these things are overlapping, all of this node data is basically corrupt. I've got two different path searches that are simultaneously writing in what's the best time. One's writing the best time from here, and the other one's writing the best time from there. Let me change the color of that to make that a little more clear. Okay, so yeah, this guy is writing in a certain node, what is my best time from there, and this thread's writing what's my best time from there, and the reaching edge and so on. This is chaos, right? You have one global variable that is trying to store two different things. The results are two different path searches at the same time. In fact, it's going to be four. I only drew two, but you're going to have four of them. So this is not going to work, okay? And I showed this in the tutorial from this week. What happens is actually kind of hard to predict. Sometimes your program hangs. Sometimes it gets a memory fault and crashes. It's difficult to predict because your threads are just doing weird things to memory and all sorts of crazy stuff can happen. Challenging thing to debug. So the solution, which Trevor has basically already pointed out, is make this local. So do not declare this as a global variable. If you instead declare it inside this function, then it's a local variable that was declared within the for loop. I mean, it's within a function called by the for loop, which is fine. So in that case, you're going to get 4 copies of it, one for each of the 4 threads, and it's going to work perfectly fine. Okay? So be careful about this. Be careful about writing to a global variable in multiple threads. It's okay if everybody's reading from it. So you might have cached all sorts of data in your m1.cpp and it's global. If nobody's updating that, it's okay. But if somebody's updating it, and for this data, we are updating it in our path search, that's not okay. Got to make it a local variable. The other option you can do to stop multiple writing is use OMP Critical, but as I said, that's not as desirable. It limits your speed up. It's more complicated to code. And in this case, with OMP Critical, if I put an OMP Critical around, well, whatever code was accessing this deep inside this routine, if I put an OMP Critical around that, would it fix the problem? Yeah, so that would not fix the problem. So putting an OMP Critical around it wouldn't fix the problem. And the reason it wouldn't fix the problem is we have a bigger problem than just 2 things might be writing this at the same time. They're also trying to write different things, right? One of them is trying to update what's the best time from here. Another is trying to update what's the best time from here. They're trying to store different data. So even if you put it in an OMP Critical, it just does not make any sense. You need 4 copies of this. Okay, so that's how you multi-thread. But I want to warn you to keep things simple. So don't try multi-threading until you have a good serial implementation, because it is harder to write multi-threaded code. It's harder to debug it. You do not need to multi-thread to have a good implementation. So most students are not going to write a multi-threaded version of this, and that's perfectly fine. This is like an optional thing if you're like looking for an extra challenge, want to learn about it. It is an important programming technique, so it's not bad to get experience with it, but only do that if you have the time and it's not going to be unduly stressful. And you have a serial algorithm to fall back on. Okay, some resources. There's a tutorial here on OpenMP, some information on how to debug with threads, and tutorial 9, I basically went through in a much more hands-on way what can go wrong when you do this and what are some debugging techniques. Okay, if you want to learn more about this, computer systems programming is about how you make programs go fast. So how to profile them, how to write code that is compiler friendly, and how to use parallelism. So kind of all the things that we talked about in this course, but in much more depth. 344 operating systems will show you what is a thread in more detail. How do operating systems actually run these things? And then in computer architecture, ECE 552, you'll learn about how do you create CPUs that can run programs fast, both on one core and also having multiple cores collaborate. So there's a lot of really interesting hardware design problems there. Okay, and that is the end of what I had to talk about today. Let me stop recording here. And I'll stay on the line